Hello, and welcome to today's lesson on L'Hopital's rule. We're going to introduce what L'Hopital's rule is and do some examples, and then there are other videos that get into other versions of indeterminate forms that follow this. But for right now, what is L'Hopital's rule? Well, if we have two differentiable functions, function f and function g, on an open interval containing some value of x equal to a, some number, then the limit of each of these functions as x goes to a, they're both equal to 0. Then we can find the ratio of the limits by finding the ratio of the limits of their derivatives. So if we have an indeterminate form, okay? So the first indeterminate form we're going to work with is, what if we have a problem where we have a 0 over 0? So let's look at why this rule works, first of all. And the reason it works comes out of some algebra here. If we look at roughly the definition of derivative of function f at point A, it's a slope. It's the derivative function will be the function minus the value at a over x minus a. Same thing for g. So we make a ratio of these two. And when we go through all of this algebra, and what we found out was, the reason we're doing this is when we plug a into function f, we get 0. And when we plug a into function g, we get 0. So in the example on the left, if our function f was red, the red line, and our function g was the blue line, well, it turns out if you find the equation of this line, the red line clearly has a positive slope, and let's see, you go a rise of 2 for a run of 4. That's going to give you a slope of 1/2 x, and the intercept is a positive 2. And for line G, it has a negative slope. You can see that it's going downward. And it also, for a run of 4, it actually has a fall of 2, so the slope is negative 2/4 or negative 1/2. And it has a y-intercept of 2. So those are our two functions. Now, if I look at f of negative 2, for both of these functions, I get 0. Sorry, not f of negative 2. It should be f of negative 4. Let me fix that. F of negative 4 is 0. So in our case, in our example we're going to do here, our a is negative 4. And you can see that on the graph of these two functions. If I plug a negative 4 in for x in function f, I get 1/2 times negative 4 plus 2. It's a negative 2 plus 2. That's 0. I will have something similar happen here when I use x in function g. Here I get a positive 2 minus 2, which is also 0. So if I were asked to find the limit as x goes to negative 4 of f of x over g of x, then the substitution attempt would result in 0 divided by 0. That's called an indeterminate form. So we have that case with these two functions. But if I look at what the derivative of the red function means, it just means the slope of that line. And the derivative of the blue function just means the slope of that line. Well, the slope of the line can be given by these functions here. At any point x, subtract f of a, and f of a is 0, g of a is 0. And when we finish doing that, it turns out, okay, the limit of the ratio of our two functions as x approaches our negative 4 is the same as the limits of their derivatives taken individually as a ratio. So what that really means is I can do the limit, it's going to be the same as the limit as x approaches a of f prime of x over g prime of x. So this is not the quotient rule for taking derivatives. We are literally taking the derivative of the top, derivative of the bottom, and making a new ratio. And in L'Hopital's rule, what allows us to do that is the fact that when we tried substitution, we got one of these indeterminate forms, 0 divided by 0, particularly here. So for our two functions in red and blue here, well, the slope of a line is constant. So the derivative of f of x is just its slope. The derivative of g of x is just the slope of that line. So what I get is the limit as x goes to a of 1/2 divided by negative 1/2, and it turns out this limit would be a negative 1. So I would be able to use that information. I would be able to take the ratio of the derivatives and get the limit. The limit does exist, and it's negative 1. Now, if I made a composite function of the ratio of these two lines, if I actually graphed the ratio of these two lines, you would be able to see that the limit as x goes to negative 4 is negative 1. It would be a point discontinuity because it's a 0 of both the top and the bottom, but it would just be a hole, therefore the limit would exist. And the function value that would fill it in to make it continuous would be y equals negative 1. But so here's a summary. If you get an indeterminate form, in this case we're working with 0 over 0, there are other indeterminate forms, as we see here. If we get infinity over infinity or 0 times infinity, and these forms will need to be rearranged. We're not going to do much with these in class. I'm just giving you the basic indeterminate forms. These end up being rearranged to become a 0 over 0 or an infinity over infinity. Then you can use L'Hopital's rule to take the limit. Now, you've learned how to do some of these limits before. You could have done this with a table of values. You would have approached x equals negative 4 both from the left and the right and seen that you were converging upon a function value or a limit value of negative 1. So you can do these using a table if you get this indeterminate form too. But this ties back. So I'm going to erase this here. You could always rewind the video. I'm going to try to erase what I have here. This ties back to what we did when we found limits of rational functions. And I'm going to make an example that we could factor out something over the top and bottom. If we got 0 over 0, we looked to see if we could factor. Well, this is kind of an expansion of that to include other cases where you get 0 over 0. It doesn't have to be a rational function. So we have in the past done things like the limit as x goes to 3 of x minus 3 over x squared minus 9, for example. I put 3 in the top. If I do 3 minus 3, I get 0. If I do 3 squared minus 9, I get 0. I get that indeterminate form. So in the past, we have done x minus 3 divided by x minus 3 times x plus 3 because these were nicely factored. And that gives you a 1 on top, and then you do 1 over 3 plus 3 is 1/6. L'Hopital's rule is now telling us we could just take the derivative of the top and the derivative of the bottom, and we could change our problem to become, let me give myself more space here. So the limit as x goes to 3 of x minus 3 over x squared minus 9, which was our original problem, by L'Hopital's rule is the same as the limit as x goes to 3 of the derivative of x minus 3 is a 1. The derivative of x squared minus 9 is 2x. And sure enough, when I substitute there, I get 1/6. So this is another way to handle those cases where you get 0 over 0. Before, we were limited to only being able to handle them when we had things that factored out. But this allows us to find the limit of functions like sine x over x. And that sine of x at x equals 0 would be 0. X would be 0. You can take the derivative of the top, derivative of the bottom, and find out that that limit is actually a 1. So we're going to see some examples in a moment. That is the introduction to L'Hopital's rule. And now we're going to move on into some examples.